Every electrical system can fail. During an electrical fault, high fault currents of up to several thousand amps can occur. Such fault currents need to be interrupted by a protective system. The simplest form of overcurrent protection is a fuse. In the event of a failure, the inner conductor of the fuse will melt and interrupt the current flow. Fuses can only be used once, and the maximum current that a fuse can interrupt is limited. Thus, fuses are only used in low-voltage systems and in some medium-voltage systems. High-voltage systems use a protective system consisting of circuit breakers, current transformers, and protective relays instead. The current transformer transforms the primary current into a smaller current that is fed into the relay. That current is called the secondary current. If this current exceeds the pickup value for a specific duration of time, the relay will issue a trip command and cause the circuit breaker to interrupt the current path. The relationship between the pickup current and delay time is defined by the tripping characteristic curve. An inverse tripping time curve indicates that the relay will trip increasingly faster due to higher overcurrent. There are different types of inverse time curves, such as long time inverse, normal inverse, very inverse, and extremely inverse. Other than inverse time curves, definite time curves assign the same delay time to all of the overcurrents that exceed the pickup value. In our curve example, that means that the trip time is the same for a 10-fold overcurrent and a 100-fold overcurrent. The definition of an instantaneous curve is when a relay is operating at its maximum tripping speed after the pickup current has been exceeded. That means that the relay trips as fast as it can for very high currents. Modern relays usually combine different curves within one housing. The complete protection system also includes elements residing in a number of other relays. All protective elements need to work together in order to form a selective system. For instance, when a fault occurs here, it should not affect the electrical supply of customers in the neighboring segment. Only the affected segment should be switched off. Thus, only this relay should trip. This is achieved by setting it to work faster than the relay in the neighboring segment. For a specific fault current, the red relay would have a longer time to clear a fault, so the yellow relay clears it first, and so the fault is cleared before the red relay would react. Typically, a protection relay may wait for years for a fault to occur. But when a fault does occur, they need to operate reliably and fast. In order to ensure this, operators run tests on the protective relays. During testing, a relay is disconnected from the current transformer and connected to a test set instead. In order to simulate load conditions and fault currents of up to a few thousand amps, the test set generates a current that represents the secondary current of the current transformer. The test set timer records the relay's trip time. Depending on the magnitude of the test current, the relay must not trip, or it has to trip within a certain time. The results need to be documented in a test report. Let's hope that dealing with a fault is something your relay never has to do.